Hi, welcome to lecture 14 of solitons. Last time we introduced a solution generating technique known as the Backlund transform, which allows us to move from the solution of a differential equation P of u equal to 0 to the solution of another differential equation Q of v equal to 0. And the machine that allows us to do this is the Backlund transform, which is given by a pair of relations between the field u, which satisfies the first differential equation, and the field v, which satisfies the second differential equation. And this is a so-called Backlund transform. Whenever given a u that solves the first differential equation p of u equal to 0, we can solve the pair of equations that define the Backlund transform, this pair of relations, to find the v which solves the second differential equation Q of v equal to 0. And vice versa, given a solution of Q of v equal to 0, we can solve the system of equations that define the Backlund transform to find the u that solves the equation P of u equal to 0. Then we apply this idea to an example in which P and Q were the same differential operators. In that case, we call this an auto-Backlund transform. And in the example, the two differential operators were the sum of the second derivatives with respect to x and with respect to y. So we found that u and v satisfied the Laplace equation. And then later on, we moved to the Sine-Gordon equation. And in particular there, we wanted to introduce an extra parameter, which here we called A. And that parameter allows us to find new solutions whenever we keep applying the Backlund transform. So in the previous example of the Laplace equation, if we apply the Backlund transform twice, we would go back to the original solution. And the same thing would happen for the Sine-Gordon equation if it weren't for this parameter A. So the equation 5.8 here defines the Backlund transform. So we have once again a pair of relations between u and v that you see there in the box. And what we saw is that actually this pair of relations implies an equation for u, which is the Sine-Gordon equation, u plus minus equal to minus sine of u. And also an equation for v, which is the same equation, the Sine-Gordon equation, now written for v. So it's v plus minus equal to minus sine of v. And in this particular case, we didn't need to use one differential equation to obtain the other differential equation. So this is not always the case, but it's true for the Sine-Gordon equation. So what we will do today is to put this auto-Backlund transform for the Sine-Gordon equation to good use. And in particular, we'll start by looking at the first example in which we'll use the auto-Backlund transform to rederive the one-soliton solutions of the Sine-Gordon equation, namely the kink and the anti-kink solution that we have obtained previously with a number of different methods. So let's do that. I'm going to go to full screen now. So here we go, section 5.4. We look at our first example, the Sine-Gordon kink from the vacuum. As you can probably guess from the title, what we will do is to take the seed solution, our input in the Backlund transform, to be the vacuum solution v equal to 0. And then the auto-Backlund transform 5.8, which you can see above, simplifies. So in particular, the first equation is u plus equal 2 over a sine of u over 2. And the second equation is u minus equal to minus 2a sine of u over 2. So we view this pair of relations as a system of differential equations, and we're going to integrate the two equations by separation of variables using the integral of du over sine u over 2 is equal to twice log of the tangent of u over 4 that we have used already a number of times. So when we integrate the first differential equation, which involves a derivative with respect to x plus, we find that 2 over a x plus is equal to 2 log tan of u over 4 plus an integration constant, which is constant with respect to x plus, but in general will depend on x minus. So I'll call that f of x minus. And similarly for the second equation, where the derivative is with respect to x minus, we get minus 2a x minus is equal to 2 log tan u over 4 plus an integration constant g that now depend on x plus, the other variable, which is a spectator. This is equation 5.13. Now let's subtract the two equations and rearrange terms on the two sides. So when we subtract, 2 log tan u over 4 cancels out. And I'm going to write terms which depends on x plus on the left-hand side. So we'll get 2 over a x plus g of x plus. And this is equal to minus 2a x minus plus f of x minus. Now, with this rearrangement, it's clear that the left-hand side is a function of x plus only. The right-hand side is a function of x minus only. But the equation tells us that the two sides are equals, and since the left-hand side does not depend on x minus, the right-hand side does not depend on x plus, being equal, the two must be equal to a constant, which I will call, for later convenience, minus 2c. Therefore, to summarize, we find that f of x minus is equal to 2a x minus minus 2c, and similarly g of x plus is equal to minus 2 over a x plus minus 2c. And so if we plug this back into equation 5.13, we find that 2 log tan u over 4 is equal to 2 over a x plus minus f of x minus, so we get minus 2a x minus plus 2c. Now we can get rid of the common factors of 2 and invert the previous expression to find u that would be equal to 4 arctangent of exponential 1 over a x plus minus a x minus plus c. This is equation 5.15. Finally, let's convert this to x and t coordinates. So we have 1 over a x plus minus a x minus. I'll drop the integration constant for this calculation. So we get x plus is t plus x over 2. So the first term is 1 over 2a t plus x. X minus is t minus x over 2. So the second term is minus a over 2 t minus x. And now I can collect the terms which multiply x. So this will be a over 2 plus 1 over 2a. And I can also collect the terms which multiply t. I'll write a minus sign in front, and I get a over 2 minus 1 over 2a. Finally, let's extract the coefficient of x as a common factor. By writing a common denominator, I can write that as a squared plus 1 over 2a, and that multiplies x minus the coefficient of t was a squared minus 1 over 2a. So taking into account a common factor in front, we get a squared minus 1 over a squared plus 1, and that multiplies t. So if we define the following quantities, so first we have v, the velocity, that's what comes in front of t in the expression x minus velocity times t. So that will be a squared minus 1 over a squared plus 1. Then I'll define a sign epsilon, which is the sign of the parameter a. And finally, given the velocity, I can calculate the Lorentz factor gamma, which is 1 over root of 1 minus v squared. And if you plug in the previous expression for v given in terms of the parameter a, I'll leave this as an exercise, you will find that this is equal to 1 plus a squared over 2 absolute value of a. That's equation 5.16. With this definition, the solution 5.15 which we generated by applying an auto-Backlund transform to the vacuum, reads as follows. We have u function of x and t is equal to 4 arctangent of exponential epsilon times gamma x minus x naught minus v times t. Where we traded the integration constant c for x naught. The solution will hopefully look familiar by now. This is nothing but the kink or anti-kink solution of the sine-Gordon equation. It's a kink if epsilon, the sign in the exponent, is plus 1, and it's an anti-kink if epsilon is minus 1. Now let's study the properties or the behavior of this solution depending on the parameter a. So first, let's look at the sign of a, which determines epsilon. So when a is positive, epsilon is equal to 1, and this solution is a kink. On the other hand, when A is negative, epsilon is equal to -1, and the solution is an anti-kink. On the other hand, the sign of the velocity is controlled by a squared. So if a squared is larger than 1, or in other words, if absolute value of a is larger than 1, the velocity is positive, which means that the soliton is right moving. Conversely, if absolute value of a is less than 1, the velocity is negative, which means that the soliton moves to the left. We can summarize this with the following table. So there are 4 cases depending on the range of A. So if A is less than -1, then we get a right-moving anti-kink. If A is between -1 and 0, we get a left-moving anti-kink. So notice in particular when A crosses -1, the direction of motion of the soliton changes. So then when A is between 0 and 1, the soliton is still left moving, but now it's a kink. So it's the topological charge which has changed now that we have crossed A equals 0. And finally, when A becomes larger than 1, the soliton remains a kink, but now it is right moving. The important point here is that the Otto-Backlund transform applied to the vacuum created a kink or an anti-kink. And if we vary the parameter A of the Backlund transform, as long as that's different from 0 or infinity, in which case the solution doesn't make sense, and we also vary the integration constant, x0 or c, we can reproduce all the kink and anti-kink solutions that we derived earlier by other methods, for instance, as traveling waves. This is very interesting. If we apply the Otto-Backlund transform to the vacuum, we create a kink or an anti-kink. But what is even more amazing is that this holds more generally. Namely, the Otto-Backlund transform applied to a solution of the Sine-Gordon equation always adds a kink or an anti-kink. So in general, we can think of the Otto-Backlund transform as a solution generating technique. Which adds kinks or anti-kinks. I wrote add in quotes, in quotation marks, because this is not a linear equation. The Sine-Gordon equation is not linear. So the linear superposition principle doesn't apply, but still every time we apply an auto-Backlund transform, we get an extra kink or anti-kink in the solution. And in the following, I'll use the following diagrammatic notation where we start from a seed solution U1, then we apply a Backlund transform with parameter A and say integration constant C. Later on, I will not keep track of the integration constant in the diagram. And what we get is a new solution U2 of the Sine-Gordon equation, which contains an extra kink or an anti-kink. So earlier I called one of the solution U and the other solution V, but now I'm gonna use U1, U2, U3, etc. From now on. So notice that we can add the kink or anti-kink wherever we like, depending on the integration constant C, and with whatever velocity we like, depending on the parameter A. For example, another example of such a diagram would be the following. So we can start from a seed solution U0, then we apply a first Backlund transform with parameter A1 to get the solution U1, then we could apply another Backlund transform with parameter A2 to get the solution U2, and finally a third Backlund transform with parameter A3 to get the fourth solution U3. So this diagram would represent the addition of three kinks or anti-kinks to the seed solution U0. So whether we add the kink or an anti-kink, in fact, depends on the seed solution. We'll see more about this later. Okay, this is all very nice. So we have a new machinery, the Backlund transform, which allows us to add the kink or anti-kink to find new solutions of the Sine-Gordon equation, which is nonlinear. The trouble with this is that every time we do a Backlund transform, we would like to integrate the two relations, the pair of relations that define the Backlund transform. And it turns out that the integrations get harder and harder as we keep adding solitons. But luckily for us, there is a nice theorem which comes to a rescue. And that's what we're gonna look at next. This takes us to section 5.5, the theorem of permutability. Let's apply two consecutive Backlund transforms. With parameters A1 and A2. So we'll start from a seed solution U0. So then either we apply Backlund transform with parameter A1, and we get to a new solution called U1, or we apply a Backlund transform with parameter A2, and we get to a different solution U2. So for each of these two choices, then we can apply the second Backlund transform with the other parameters. So from U1, we can go to U3. If we act with the Backlund transform with parameter A2, and from U2 we can go to U4 if we act with the Backlund transform with parameter A1. In both cases, the final results, namely U3 and U4, look like the seed solution U0 with two added solitons with parameters A1 and A2. So you might ask, could these two solutions, U3 and U4, actually be the same solution? And the answer is yes, thanks to a theorem due to Bianchi. In 1902. The theorem states that for any U1 and U2, the constant of integration in the second Backlund transform which generate U3 and U4 can be arranged in such a way that U3 is equal to U4. In other words, the A1 and the A2 Backlund transforms can be made to commute. Diagrammatically, we can express this as follows. We start with the seed solution U0, then we act with the Backlund transform with parameter A1 and get to the solution U1. Then we act with the Backlund transform with parameter A2 and we get to U3. Or we start from U0, we act with the Backlund transform with parameter A2 and get to solution U2. But then when we act again with the Backlund transform with parameter A1, we get back to the same solution U3. So I'll spare you the proof of this theorem, which is a little involved. Hopefully the statement makes intuitive sense given the soliton content of U3 and U4. So they both look like U0 plus two added solitons. Instead, we'll focus on the application of this theorem which stems from the fact that we have two ways to get from the seed solution U0 to the final solution U3. So either through the intermediate solution U1 or through U2. So what we'll do next is to compare these two ways, and by doing that, we'll be able to get rid of all derivatives and obtain an algebraic relation between U0, U1, U2, and U3. So next, let's compare these two ways of getting from U0 to U3. So let's start by considering the part of the Backlund transform that involves the x plus derivative. And let's first look at the upper root. Namely, we start from u0. We apply Backlund transform with parameter a1 and we get to u1, and then we apply Backlund transform with parameter a2 and we get to u3. Looking back at the definition of the auto-Backlund transform for the sine-Gordon equation and focusing on the relations which involve x plus derivatives, we get that u1 minus u0 plus derivative is equal to 2 over a1 sine of u1 plus u0 over 2. And for the second Backlund transform with parameter a2, we have u3 minus u1 plus derivative equal 2 over a2 sine of u3 plus u1 over 2. And adding these two equations, we can eliminate dependence on u1 on the left-hand side and get u3 minus u0 x plus derivative is equal to 2 over a1 sine u1 plus u0 over 2 plus 2 over a2 sine of u3 plus u0 over 2. On the other hand, for the lower root, where we start from u0, apply Backlund transform with parameter a2 and get to solution u2, then apply Backlund transform with parameter a1 and get to the final solution u3, the same as above. So for this root, we can just swap a1 and a2 and u1 and u2 in the previous expression, and we'll get u3 minus u0 plus is equal to 2 over a2 sine of u2 plus u0 over 2 plus 2 over a1 sine of u3 plus u0 over 2. So we have two expressions for u3 minus u0 differentiated with respect to x plus, given by 5.19 and 5.20. And by equating them, we'll get an algebraic relation between the right-hand side. So if I divide by a common factor of 2, I get 1 over a1 sine u1 plus u0 over 2 plus 1 over a2 sine of u3 plus u0 over 2 is equal to 1 over a2 sine of u2 plus u0 over 2 plus 1 over a1 sine of u3 plus u0 over 2. So by comparing the upper root and the lower root, we obtained an algebraic relation 5.21 among the fourth solution U0, U1, U2, and U3. And this is very useful. Indeed, starting from the vacuum for U0 and the one-soliton solutions for U1 and U2, we can now generate two-soliton solutions U3 algebraically by solving equation 5.21. And then we can iterate this procedure, say starting from a one-soliton solution U0, then having U1 and U2 being two-soliton solutions, so we'll get a U3, which is a three-soliton solution. And so on and so forth. So then you can also get four solitons, solutions, etc. So what we found by looking at the Backlund transform of the sign-Gordon equation and by using this theorem of permutability that tells us that there are two ways of getting the same solution by a double Backlund transform is in essence a form of a nonlinear superposition principle. Namely, a machinery that tells us how to add, and here I have add in quotes because we don't literally add the solution, but tells us how to add solutions of a nonlinear equation for which the standard superposition principle doesn't hold. But we can use equation 5.21 to produce a new solution with extra solitons. That's all for today. Next week, we will first look at the part of the Backlund transform, which involves x minus derivative, to make sure that everything is consistent with what we obtained today. And then we will apply this idea to find the two soliton solutions by using equation 5.21 together with the vacuum solution and our knowledge of one-soliton solutions. And then we will study the properties of this new solution U3 that we will find and show that indeed it actually contains two solitons. Have a good weekend and see you next week.